at Princeton Physics, one of my favorite classes was the undergraduate advanced physics lab, where we actually used the hydrogen 21 centimeter line to map out the Milky Way using the hyperfine transition of hydrogen, which is effectively hydrogen has a proton and an electron. If they're spinning parallel to one another versus when they're spinning opposite to one another, that difference in energy corresponds to a particle of light, a photon, that is exactly the wavelength 21 centimeters or around 1420 megahertz, right? There was a radio telescope on the roof of the physics department that we could use to point it in different directions, and we could point it at the galactic disk of the Milky Way, and you could see the 21 centimeters, and you could actually figure out what part of the galactic disk was moving away from us versus moving towards us by pointing it in different directions, and that 1420 megahertz would be a little bit red shifted or a little bit blue shifted depending on where you were looking. And what you could do, I mean, there's a lot of error, right? Because you don't know exactly where you're pointing. It's kind of a, old disc that they were like, okay, let the undergrads, use it for their lab. But you could actually, I remember calculating the rotation curve, which is depending on how far away I am from the galactic center, how fast is the stuff moving. And you could actually chart out the galactic rotation curve, and you could see that the galactic rotation curve plateaued. The data that I got had massive error bars and only 8 data points. But what you could see is that it would rise and then it would plateau. Yep. And this is characteristic of dark matter. Vera Rubin, the astronomer, actually used these galactic rotation curves to calculate dark matter, because if you think about it, the farther away you get from a galaxy center, the slower you should be moving.
Right.
Because Newton's laws, inverse square law. Here, the farther you get away, you're still moving at the same rate. The only way this is possible is if there's a bunch of invisible matter that's actually pulling on you, that's creating this gravitational force.
That's sustained, that creates that plateau of sustained speed, because otherwise, there's no other external factor that could be.
Yeah, because we don't see any stars, and yet you're telling me that there's a bunch of new mass that's pulling on you.
Because you're farther and farther away and your speed has not changed.
Yeah.
Even though it should now be slower because you're farther away from the gravitational center.
Exactly.
So that gravitational force
must come from something.
It has to come from something.
And that's where sort of, dark matter, it makes sense. There's a lot of other avenues of research that actually point to dark matter, but this is one of the really cool ways of showing, there's got to be something there that we're not seeing. And it's something that an undergrad can figure out,
right,
using a shitty radio dish on the roof of Jadwin Hall. That was one of my favorite 2 weeks, was actually doing this experiment and then writing the report.